Okay, what we're going to do in this mini lecture is just a brief overview of Orris's example on page 197 and 198 in the text, where he provides a numerical example for one-factor ANOVA. What I want to make sure that we do at this stage of the process is that you really understand conceptually what we do in the one-factor ANOVA process, so that it becomes more than just looking for p-values and deciding whether to reject or fail to reject the null hypothesis. So in the setup for this example, Orris is testing tires, and he has 4 different types of tires, which he calls alpha tires, beta, gamma, and delta tires. Okay, so for the alpha tires, he actually had 5 cars. On one car, the alpha tires made it for 46,000 miles. On another car, the alpha tires made it for 55,000 miles. On the third car with alpha tires, those tires lasted for 49,000 miles. Okay, so we have a sample of tires for the alpha brand. For beta, we only had 4 cars. One car lasted. The tires lasted 73,000 miles with beta tires. On the second car, the set of beta tires lasted 61,000 miles. And then you can see here on gamma and delta. So one thing that I want to emphasize here is that when we do ANOVA, you don't need to have the same number of observations for each group. We don't have to have the same number of, in this instance here, sets of tires for alpha, beta, gamma, and delta, unless you've got different sample sizes here. Okay? So each of these numbers represents how many thousands of miles a set of tires lasted, whether those tires were alpha brand, beta, gamma, or delta brand. Okay? Then we look at the null and alternative hypothesis. Our null hypothesis is that there's no difference between the 4 brands of tires. So our null hypothesis is essentially that the average life for a set of alpha tires is equal to the average life for a set of beta tires, is equal to the average life for a set of gamma tires, is equal to the average life for a set of delta tires. Okay? So the null hypothesis is that regardless of the brand of tire, those tires all last about the same number of miles. Our alternative hypothesis, we write it as this. The average life of alpha tires is not equal to the average life for beta tires, is not equal to the average life for gamma tires, is not equal to the average life for delta tires. However, I want to be careful to emphasize here that what this really means is that not all the tires are equal to one another. In other words, it could be such a thing that alpha, beta, and gamma tires have the same average life as one another, but that differs from the average life for delta tires. Or it could be that alpha, gamma, and delta tires all last the same number of miles, but that happens to differ from the average tire life for beta. Okay? So while this is the correct way to write it, we want to make sure that we understand that not all of the means have to be different from one another, but at least one of the means has to be different, in this instance, from the other 3. Okay? So then when we go from the individual data that we collected here, and this is all in your book, like I say, I think it's page 197, 198. The alpha tires, we had 5 cars, and the average tire life for each set of tires was 51,000 miles. The beta tires, on average, a set of tires lasted an average of 63,800 miles. Gamma tires lasted just a little bit less, 61,300 miles. And then delta tires only lasted for 46,800 miles. So we're not interested here in whether our sample means are equal to one another. We expect each of the sample means to differ from one another, even if the population means are equal. We expect the sample means to differ because of random variance in collecting our samples. So the key question is not, are the sample means equal? The key question is, do the sample means differ small enough that they really come from equal populations, or are these sample means different enough from one another such that we would conclude that at least some of the population means differ? And again, just looking intuitively here, with beta tires lasting longer than delta tires, it would seem like if we're going to get a small p-value here, minimally it would be because the beta tires lasted, what, about 17,000 more miles per set of tires than the delta tires. Oh, and I should also mention, while this is the group mean for the alpha tires, this is the group mean for the beta tires and so forth, the overall mean across all sets of tires was 55,500 miles. Okay? Now, earlier in the semester I emphasized how important it was to calculate variance, and in ANOVA we come back and we reopen this notion of working with variance. However, when we do ANOVA exercises, not only is our task to calculate variance, but it's also then to what we call partition the variance. And let me just share some notation and some equations with you. Total variance, going back to homework number 1 and exam number 1, you know how to calculate total variance, and that's denoted, I think as we did clear back earlier in the semester, as SSX. That stands for sum of squared deviations. Then in chapter 11, we will show you how to calculate what we call error variance, denoted as SSE, and treatment variance, denoted as SST. Okay? Such that we partition the total variance into two groups, error variance and treatment variance, such that our total variance, SSX, is equal to our treatment variance, SST, and our error variance, SSE. Now, although I didn't write it on the board, let me tell you that you will hear me use the terminology, and you'll read this in statistics books and financial books quite a bit. Whereas we refer to this as sum of squared treatment, and this is sum of squared errors, oftentimes you'll hear me refer to this as the SSE, I'll refer to that as variance within the groups, and SST, you'll hear me refer to that as variance between the groups. Okay? To the degree that the average tire life across all 4 brands, to the degree that the average tire life across all 4 brands is equal to one another, you'll actually get a large value for sum of squared error and a small value for sum of squared treatment. As I'll show you in an exercise in Excel, if there was no variance in each of the groups, in other words, if all of the cars that had alpha tires got exactly 51,000 miles tire life, if all the cars that had beta tires got exactly 63,800 miles, if all of the cars with gamma tires got 61,300 miles, and if all of the cars with delta tires got 46,800 miles. So in other words, if there was no variance within each of these groups, then SSE would be 0, sum of squares error would be 0, and in that instance SSX, sum of squared total, would equal SST, sum of squared treatment. So again, my purpose here was just to try to do a clear job of setting up this exercise in the text, because I see this exercise as really, really critical to first understanding ANOVA from a conceptual standpoint before we get on to the computational standpoint. And remember, as I mentioned in class, the reason why we have to do ANOVA here rather than a difference of means test is because difference of means can only handle 2 groups. So if here, rather than working with 4 sets of tires, we were only working with 2 sets, we could do a 2-group difference of means test. If we only had alpha and beta tires, we wouldn't have to do ANOVA. We could do a two-group difference of means test. Or if we had only alpha and delta tires, two groups would be a two-group difference of means test. But because we have four groups, alpha, beta, gamma, delta, because we have four groups, that exceeds the capacity of the two-group difference of means test, and that's why we have to run ANOVA. And what are we interested in finding is, do any of these tire brands, alpha, beta, gamma, delta, do any of these tire brands last longer than the other tire brands?